Now that we have a foundation in working with the singular value decomposition, we're prepared to see how powerful this can be in working with images and compressing images. So first of all, recall that we can decompose a matrix of size m by n, this does not have to be a square matrix, into a factorization of three matrices, U times sigma times V transpose. And the dimensions are m by m by n, and n by n. And when we multiply those together, we reconstitute the A matrix. Now we've also written it in the vector equation form as a vector equation, which does the exact same thing, but allows me to break apart the A matrix into individual terms. So here we have some A matrix that we're trying to represent. And when we multiply these vectors, recall that this is a product of an m by 1 vector P by a 1 by n vector V1 transpose, which in and of itself gives me an individual m by n matrix. And then when I scale it by sigma, that has a scalar effect. And same thing here. And for all of these terms, we have individual m by n matrices. Now, when you aggregate them, when you add them all together, you get back the original A matrix. Each of these terms is often referred to as a principal component, and this can be called principal component analysis that we're about to do here. Now imagine that we omit some of these terms. If I were to say only take the first term of this vector equation expansion of A, and I were to sort of chop off these extra terms here, then what I would get instead is an approximation of A. I'm writing approximately equal to, because if I only kept, say, the first or second principal components, then I wouldn't quite reconstitute A in its entirety. So it's sort of like saying if I take the number 7 and I write it as 6, or say 5 plus 1 plus 1, and I only keep the first term of that expansion of 7, then I can say, well, 7 is approximately equal to 5. Now, what do we mean by approximately? In this context, we're just saying that we're trying to approximate the original value by means of collecting some or more of the terms. Now, clearly, the more of these terms that I keep, if I also add in the second term, then 7 is closer to 6 than it is, or 6 is closer to 7 than 5 is to 7. And then, of course, if I keep all three of those terms, then I get 7 equals 7, and I get the entire, I reconstitute the entire value. With matrices, it's no different. We're just adding a bunch of components at the same time. So this vector equation here tells us that an image represented by A can be decomposed into individual m by n matrices that, when added up, reconstitute the entire image. Well, we've just observed what happens if we only keep some of the terms. Let's go ahead and look back at our running example. Our original matrix A was this 2 by 3 of values 2, 0, 4, 0, 4, 2, and we were able to kind of get this little image to represent or reflect that matrix. Now, if I only kept one term of the expansion, this is going back to our original computation of the eigenvalues and eigenvectors of A transpose A. And remember again that these are, the eigenvalues and eigenvectors are of A transpose A. Since A itself is m by n, then it follows that A transpose times A transpose is an n by m matrix, A is an m by n matrix, so the product that I end up getting is an n by n square symmetric matrix. When you multiply a matrix by its transpose, you not only get a square matrix, but you get a symmetric one. Beautiful result. Now, from our computation, if I were to say, I want to approximate A by only keeping the first sigma I, or sigma 1, times P1 vector times V1 transpose, and these were the three components there. and I multiply them together, I get the matrix 1, 2, 3, 1, 2, 3. Now, what we're trying to do here is we're trying to approximate the 2, 0, 4, 0, 4, 2 matrix. Now, clearly that's not a great approximation, just kind of like 5 is not a great approximation of 7, but it somewhat aligns, right? It's still kind of, some of the components line up. Some of them didn't quite get the correct shade because a value of 2, we had a value of 2 here and a value of 2 here, but now that represents our second column within that image. And then we ended up with some 1s, so that was a slightly lesser shade. So you can see that it's a somewhat blurry representation. I'll call this blurry because it is a blurry version of this. Now, maybe you can't even make out what the original image was, but if this were a larger image, a picture of somebody, you'd probably still be able to make out some of the lines and some of the features of that. Maybe not very well, but you could certainly try. Now, if I kept the first 2 terms, then that's going to include the first term, the sigma 1 P1 V1 transpose, plus the second term, the sigma 2 P2 V2 transpose, and lo and behold, I get exactly the A matrix in this case. And you can see that that's the actual A right here. This is our approximation by using the first 2 terms. Now, we ended up, for this particular image, this 2 by 3 image, we actually had 3 terms. We had sigma 1 P1 V1 transpose plus sigma 2 P2 V2 transpose plus sigma 3 P3 V3 transpose. Now, in our case, sigma 3 was equal to the square root of 0. Sigma 2 was equal to the square root of, I believe, let's back up here a second, 14, square root of 12. And sigma 1 is the square root of 28. Okay, now notice that these are also described in descending order. So in our case, since sigma 3 was 0, square root of 0 is 0. This is the square root of 0 right there. Doesn't matter what P3 and V3 transpose are, it's going to result in an M by N matrix of zeros. So we'll have zeros across the board, and we often write it like this to indicate that it's just populated with zeros. And so this matrix here, since it is going to contain all zeros, is not going to actually contribute to the approximation any, but it still is a valid term in that expansion. So with 2 terms, we were able to completely gather everything we needed in order to get the original A matrix back. So one thing that we should notice here is that the more terms we do keep, or at least in this example, if we kept 1 term, we got kind of a blurry approximation. If we kept 2 terms, we got a much better approximation, in this case, an exact one. So keeping additional terms results in a better approximation of A. That's a key observation there. Now, why not just keep A in its entirety? Why not just keep the original A matrix? The nutshell reason is because the A matrix is typically going to be very large. And so if it is, say, like a standard 1280 by 720 image, and perhaps even larger, and you're going to ship that off, or some number of megapixels, 10 megapixels or 20 megapixels, that would be 20 million pixels that one would need to send. And it turns out by sending a somewhat slightly blurry image that finds the nice compromise between the number of pixels that we need to hang on to and the quality of the image, then that is often better than sending an extremely high resolution image with a large file size. Of course, it's going to depend on context as well. If you're sending it off to somebody who's going to print photos for you or print a poster board, you probably need to send the full resolution image. But a lot of times we don't need to do that, especially when we're web publishing. If you were designing a web page and you had images that were 40 megapixels on there, it would take the user a very long time to load that page, and you wouldn't get much traffic to your website. All right, so let's analyze why it makes sense to just send individual principal components. After all, if each component is an m by n matrix, then you're sending multiple m by n matrices. Not quite. We'll see why. So first of all, let's create a convention here. Let's always make sure that the way we define our lambdas, which remember that each of the sigma i's is just the square root of the lambda I, and lambda I is an eigenvalue of the matrix A transpose A. So let's make sure that we order them in decreasing order. In other words, sigma 1 is always the largest and sigma n is always going to be the smallest, kind of like we had here by default. Okay, so square root of 28 is bigger than square root of 12, which is bigger than the square root of 0. Then the terms with the largest sigmas will contribute to a larger part of the approximation of A, the original image. The smallest sigmas will have little influence on the approximation. So we see that here that sigma 3 had, in this case, no influence on the approximation of A. And this is going to be some m by n matrix, but notice that you're scaling it by a factor of square root of 28. That's going to have, this term's going to have a larger impact on that approximation because of this scalar effect. This is a larger scalar effect, and this is a smaller scalar effect. So this term, we're going to say, has a much bigger or much more profound impact upon the approximation. And any terms that from the largest contribution to the smallest contribution, any terms that have the smaller contribution will start to contribute less and less to the overall approximation of our image. All right, well, let's see why it would make sense for, say, a 1280 by 720 image. Now, this will have, if A is an m by n matrix, A is m by n, that means that in this case, it's going to be a 1280 by 720 matrix. That means that our U matrix, which is m by m, will be 1280 by 1280. Our sigma matrix will be 1280 by 720, same size as A. And then our V transpose matrix will be n by n, which is 720 by 720. So that means that there are going to be 720 different eigenvalues, since there will be 720 eigenvectors. So you'll have 720 lambda i's and 720 vi's, eigenvectors. And I know that because of the size of V, that's going to contain all of the eigenvectors of A transpose A. Now in this case, A transpose A, since A is 1280 by 720, A transpose is 720 by 1280, and A is 1280 by 720, so this will produce a 720 by 720 symmetric matrix. And a square matrix with 720 dimensions will have 720 eigenvalues and 720 eigenvectors. All right, if I sent this image out, I would need to send 1280 by 720, what we'll refer to as bytes, okay? Now, bytes are, a byte is 8 bits, and so let's not worry about the units at this moment, but 1280 by 720 will give me an image that is 921,600 bytes. Now, if if we think about file size, this is in kilobytes, 920, about 922 kilobytes. So that's less than 1 megabyte. 1 megabyte would be 1 million bytes, or 1,000 kilobytes. So this is a reasonably small file size that if you were to publish this on a website, most computers could render it very, very quickly. In fact, faster than back in the day, we used to have 56K modems that would render a picture like this. You would slowly start to see the image unfold on the screen, and you'd be waiting, you're like, what's that a picture of? And it would take a lot longer. Now you can render these files very fast. So that's a 922 kilobyte image. But suppose that instead I approximated A with the principal components. So I'm not going to send a series of matrices to somebody. Instead, what I'm going to send them are the sigmas, the p's, and the v transposes. Now, if we begin writing this out, we know that this would be sigma 1 times p1 times v1 transpose plus sigma 2 p2 v2 transpose, and so on until we get to the, in this case, 720th, sigma 720, p720, v720 transpose. So there'll be 720 terms in this expansion. But here's the cool part. Each of these sigmas, this is just one number. This is just one value. The p vectors, those are, recall, the columns of the U matrix. So you have p1 all the way up to pm. Well, I shouldn't say a plus. You'll have a series of these p vectors in here. And so since U is 1280 by 1280, that means you'll have each column, each of these columns will have 1,280 components in it. So this is going to be a 1,280 by 1 vector. Now V transpose contains the eigenvectors of A transpose A. So this is one row in there, and you'll have n of 720 of those rows. So each one of these, since this is 720 by 720, this row will have 720 elements in it. So this will be a 1 by 720 pixel image. I'm sorry, 1 by 720 valued vector. Okay, so now if I were just to send the approximation of the image given by the first principal component, and I said A720 by 1280 is approximately equal to sigma 1 P1 times V1 transpose. Now, just keeping the first principal component may be far inadequate to really produce a quality image, but here's the key. If I want to send somebody this approximation, I'm not going to send them the entire matrix that this, because this would also be a 720 by 1280 matrix. Instead, what I'll send them is one value. I'll send them my sigma 1, so send. I'll send them P1, and I'll also send them V1 transpose. So in total, what I have to, and then I give them instructions, right? I give the computer instructions, and this is where we're kind of removed as human beings. The computer does all this work for us, but this is one value. This contains one value. Then I have to send 1,280 more values, and then I have to send 720 more values. So in total, this will come out to 2,001 values that must be sent. Now that's as opposed to 921,600 values to be sent. So in this case, each term requires 2,001 values to be sent. The really cool thing here is if I want a better approximation of that image, if, for instance, I do A720 by 1280 approximated by even the first three components of this expansion, and I'll just say all the way up to sigma 3 P3 P3 transpose, then this will require, this one term will require me to send 2001 values. The second term will require 2001 values. And the third term will require for me to send 2001 values. And that in total right there is 6,003 values that need to be sent. And I'm getting a better approximation. So each additional term of this expansion, this singular value decomposition, will only cost me 2001 more values to send, and it will make sense to send as many terms as you can to render a good image, provided that it doesn't exceed the number of values that you would need to have sent to have rendered the entire image in its full resolution. So this is really cool stuff. We save a lot of memory, a lot of data is saved. And once again, what we're going to do is we're not going to send the actual matrix that gets produced by this multiplication, but instead we'll send a sigma, a p vector, and a v transpose vector. And we'll do this, we'll send as many as we need in order to render that image cleanly. So clearly, the more of these terms that you send, the more data that's going to cost you. But that's still 6,003 is better than 922,000. And perhaps we need to figure out what would constitute a good quality image. Now, there are techniques out there for that, but for all intents and purposes, we can start to explore what this would look like. So I'll show you in the next short video how this actually produces high quality and low quality images.